Okay, welcome to Let's Get to the Marks. Going through a quick organic A-level chemistry question on reflux. Let's get into it. Let's smash those exams, guys. All right, question 6. Propane 1,2-diol has the structure CH2OH, CHOH, CH3. And that's the structural formula. It's used to make the polyesters and is one of the main substances in electronic cigarettes, e-cigarettes, so your vapes and stuff. A sample of propane 1,2-diol was reflux with a large excess of potassium dichromate 6 and sulfuric acid. Draw the skeletal formula of propane 1,2-diol. This one's a nice easy one. So what I suggest, grab some paper, grab a pen, you know the coup, pause the video, scribble it out, unpause, check your answer. All right, let's go. Propane 1,2-diol. So propane means we have 3 carbons in the chain. 1,2-diol, I can put the OH group anywhere on the first or second carbon. It doesn't matter whether you start from the right or the left-hand side of the chain. The numbering always goes in the lowest possible way. So it doesn't really matter if my OHs are anywhere else. And there we go. Propane 1,2-diol. The 1,2 stands for the 2 carbons, diol for the 2 alcohol groups or hydroxide groups. Right, 6.2, write an equation for the oxidation. Write an equation for this oxidation reaction of propane 1,2-diol under reflux using O to represent the oxidizing agent. Show the display formula of the organic product, and it's 2 marks, right? So we don't need to write out potassium dichromate, which is our oxidizing agent. We just need to use an O for every oxygen we need. Now, our reactant is propane 1,2-diol, and there's a key here. So make sure you always circle and identify key things. Even in the most simple sentence, there might be something that helps you understand what to do. Okay, propane 1,2-diol. Look, they've given us we can just copy this here, right? So that's kind of groovy for us. So we got CH2. Write an equation, all right, and then show the displayed formula of the organic product. Right, I'm not going to show the displayed formula of this, but I'll show the displayed formula of the organic product. Oh my days, this is the most awful. Yeah, you know what I'm saying. I'm pretty poor at the old writing here. Okay, so there's our propan 1,2-diol. Okay, now they've said use the O as the oxidizing agent. So that is our potassium dichromate. Now, when you oxidize an alcohol, and we've got a primary alcohol here, look, this is a primary alcohol. And we've also, interestingly enough, got a secondary alcohol here because this only has 1 hydrogen attached to this carbon. So this is like a secondary alcohol, and this is a primary alcohol. I mean, it's probably easier to do it like that. That's a primary alcohol, and this is a secondary alcohol. Now, how should that affect us? Well, that affects the product that we're going to make, right? So let's zing the arrow. And this means I'm going to put the number and balance this oxygen after because I don't know how many oxygens I'm going to add yet. We're under reflux. What does that mean? That means the oxidation goes to its full maximum oxidation potential. So a primary alcohol, we can oxidize that to what? An aldehyde, and then we can oxidize that further to a carboxylic acid. So really over here, I want to change this to a carboxylic acid. Okay, so I'm going to keep my OH group or whatever, but I'm going to put a COO. So we've got carboxylic acid there. I'm sure I should have done the O up there and the OH down there. Maybe it looks a bit nicer. Yeah, whatever, it doesn't matter. Now over here, so there's my carboxylic acid. Remember, that's because this is a primary alcohol and we're refluxing it. So it's not just going to go to an aldehyde, it's going to go to a carboxylic acid. Now over here, I've got a secondary alcohol. This can only be oxidized to a ketone. It cannot make it to a carboxylic acid, and obviously it can't go to an aldehyde. It's not at the end of the chain, so it can't make it all the way to an. So I just need to put an O there, and then all I need to do for the rest of this is that's 4 bonds around there. Is just smash this all up. Now, here's the tricky bit, right? You're going to get a mark for that displayed formula for working out that. So well done to yourself. Well done to me. Woohoo. Here's the tricky bit, how many oxygens? And this takes a little bit of skill because if you look at this, first of all, you're like, right, there's two O's there. You've just added one O, Tom. It's cool. One, two, three. You've added one O. But how many hydrogens are on here? One, two, three, four. How many hydrogens were over here? Check it out. One, two, three, four, five, six, seven, eight. So we've lost four hydrogens. What's happened to those four hydrogens, guys? What have they become? Hydrogen gas? They've become water. So there are two water molecules being given away. And that means we need another two oxygens for those water molecules. So not only do I need this extra oxygen here, but I need another two there. So I need a three in front of that. And that is going to get me the second mark. So just make sure when you're doing oxidation, that counts as losing hydrogen as well, because when you lose hydrogen, they go on to form water with the oxygen. So there we go. 2 marks. Lovely jubbly. Right, let's move on. Bum, bum, bum. Don't forget to hit the like, people. It helps out the channel massively. It helps me to help you get the tip-top grades. All right, 6.3. Draw a label diagram to show how you'd set up the apparatus for refluxing. Now, a lot of people don't know how to do this. Nice and easy. It's 2 marks. All we need is a pear-shaped flask. Do we have to do a pear-shaped flask? Yeah, you could do it. You could do a round bottom. I'm going to do a round bottom flask like that. But you could do a pear-shaped flask if you prefer pear-shaped. So it's just like a heart or a shape of a pear like that if you want to do that flask. So you could do that one if you prefer. Okay, I'm going to go with the round bottom flask instead of the pear shape. So here's my round bottom flask. Up it comes here. Now what we need to do, we need to get our condenser and stick our condenser into it. So our condenser comes in like this. I need to make sure that bit's clamped tight. So you might want to stick a clamp on. That is some dodgy drawing of a clamp. There's my clamp. Oh my days, I should be typing. Now, with your condenser, you need, let's just draw that going all the way up. Okay, there's my condenser going all the way up. Right, this is the important bit. Show the walls are sealed like that. Okay, and they mustn't cross over here and they mustn't be open like that. They have to, you have to show they're completely sealed. And you want the water coming out of the top and you want your cold water coming in at the bottom like that. Leave this top open because it relieves pressure. It allows vapors to escape and stops dangerous pressure buildup. This should be sealed tight here. There shouldn't really be a gap there, but it's my crusty drawing. So I've got my clamp. You don't need to label. It doesn't want, I don't think it wants, draw a label diagram. Oh, sorry, my mistake. Yeah. Round bottom flask. You can use a pear-shaped flask here as well. This over here is my condenser. This is a Liebig condenser. Liebig! Okay, there's my Liebig condenser. And then what we're going to do here, we want water in at the bottom. Now, you will lose a mark, maybe not in this particular diagram, but when you're discussing reflux, if you don't say that the water in is at the bottom and the water out is at the top. So water out coming out here. And there's a specific reason for this. Okay, so water in, what happens is the water is pushed up against gravity and it completely fills this. Okay, completely and utterly fills this, and you get the maximum heat exchange. As this is coming up, the water's at its coldest here, we're getting the greatest transfer of heat, and this is completely filled right to the top. If the water came in here and came down, this top bit would not really be filled. And so we'd actually get more stuff escaping and less transfer of heat. Anywho, that's my diagram for the Liebig condenser. And I believe they're going to give you the marks for the condenser drawn correctly like that, not crossing over from the tube, top unsealed, and a round bottom flask like that. You probably don't need the clamp. You might not even need the water in, water out in the correct way. Yeah. Anywho, let's move on. Okay, anti-bumping granules are placed in the flask when refluxing. Suggest why these granules prevent bumping. So, where are we? Oh my days. Look, check out my flask. Yay. So what do? We stick in some anti-bumping granules, and what they do is they break big bubbles like that into smaller bubbles. And why is that important? Well, it's important that you only get small bubbles in the flask because big bubbles obviously increase pressure buildup, but they also might spit some of your reactants up here into the condenser and even out here. So we don't really want big bubbles because they'll be spitting and bubbling, shaking the equipment, rattling and rolling. And so the anti-bumping granules break up big bubbles into smaller bubbles. Anywho, I longed that out, didn't I? All I need to do is say break up large, oh my days, large bubbles into smaller bubbles. That kind of easier just to say that. Okay. Draw the structure of a different organic product formed when the acidified potassium dichromate is not in excess. So if the acidified potassium, we don't have as much of the oxidizing agent, instead of getting the carboxylic acid, we're going to get the aldehyde. So I'm going to go for that version. I'm going to go for, look, I drew carboxylic acid from the alcohol, but instead I'm going to say, well, hey, the primary alcohol, I'm going to say this just goes to an aldehyde. So it goes like that. And instead of having an OH here, I'm just going to do an H there. What was it? Propanediol. So really anything that shows it hasn't oxidized to its full potential. So I could keep the OH there if I want and just show aldehyde. There's quite a few different ones, or I could show that that's gone to ketone. So this one could go to its ketone. That's the only oxidation it can do. Or you could keep that as an OH if you like, and just show that has been oxidized to an aldehyde. So we're just showing the oxidation hasn't gone as far because there's not enough oxidizing agent. Okay. I'm just going to do that and say, well, it hasn't managed. This hasn't managed to go to carboxylic acid. So if it went to full oxidation, you get a ketone form there on the secondary alcohol. And on the primary alcohol group, you would get a carboxylic acid. I'm saying it doesn't go that far, and that is my version to get the 1 mark. But there's several options in the mark scheme. I suppose we could keep that as an alcohol there. All right. Sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.